Hello, ISA. SODALITE, a Horizon 2020 project started in February of 2019. This talk will provide an update on our initial work. SODALITE provides tools to enable simpler and faster development, deployment, and execution of heterogeneous apps in HPC, cloud, and software-defined computing environments. We are living in a software-defined world. With the increasing popularity of cloud computing power of HPC and the introduction of Edge, we need application to better use and benefit from these resources. For satellite, two key inputs are the application model and the infrastructure model. The models, along with any optimizations, are codified in an IDE, which is then deployed to an target infrastructure. In Satellite, an application ops expert models the deployment of an application on an infrastructure target. These models are translated into infrastructure as a code, and then an optimized container is built. The orchestrator enables the application deployment on multiple computing platforms like HPC, cloud, or edge. Performance of an application deployment codified as models is important. How do we optimize an application deployed to heterogeneous infrastructure with diverse compute, storage, network, and scheduler? Sodalite aims to bring a vast knowledge of performance optimization accrued by the HPC industry over decades into cloud computing and edge domains. MODAK, the application optimizer of Satellite framework, aims to support static application optimization for three major application types. An application performance can be predicted using performance models of application infrastructure. The performance models are developed by running standard benchmarks across different configurations and then building a simple linear statistical model. These models will inform how the application parameters influence the performance and the performance characteristics of target infrastructure, such as peak performance and memory bandwidth. Based on the selected optimizations in IDE, MODAK maps the optimal application parameters to infrastructure target and builds an optimized container. We support Singularity for HPC and Docker for cloud-based deployments. Here, we show the usage of Sodalite for AI training deployments. A data scientist uses the SODALITE IDE to build the application model with input data, configuration, and optimizations. The application written in a high-level language or API like Keras or ONX is then deployed with a selected AI framework with optimized libraries like MKO, QDNN, compilers like XLA, GLOW, and then packaged as Docker or Singularity container. This is then deployed to HPC with the support of batch schedulers like Slurm or PBS or using Kubernetes OpenStack for cloud. In the next few slides, I'll show you some of the initial results of our experiments with deploying singularity-based containers for AI frameworks. In all these slides, y-axis is the wall clock time in seconds. In this chart shows the performance of different AI frameworks for an MNIST CNN training workload in CPU only. PyTorch, TensorFlow 1.4, MXNet has similar performance, and TensorFlow 2.1 seems to have improved a lot with recent upgrade. CNTK is not optimized for CPU. Here, we show the performance of AI frameworks that are custom built from source and optimized for x86 and NVIDIA GPUs. On the left shows the time taken to train 10 epochs of MNIST CNN network on a CPU, and on the right shows the average time taken to train one epoch of ResNet 50 network on a single GPU. For TensorFlow 2.1, we get a slight improvement, whereas for PyTorch, we get almost 17% speed up for the MNIST. For GPU running Renus, we get only 2% improvement. We are confident that this can be further improved. Here, we show the performance of TensorFlow with graph compilers XLA and ngraph. XLA is supported in most versions of TensorFlow, whereas ngraph works only in 1.4. For MNIST on CPU, XLA slows the application, whereas ngraph improves the performance by 30%. For ResNet on GPU, XLA improves the performance by 9%. These results from benchmarks are then codified to application model, which can then be used to optimize most AI application deployments. And thank you.